Now let's look at average velocity. So average velocity, you use it to describe a complicated trip. So we told you what velocity is, essentially. Now we're going to say a little more specific, average velocity. Let's just define it mathematically first. There's our script v, avg for average, and then it's delta x over delta t. So now let's think about what those mean. Let me put a box around that. That's kind of an important one there. And delta x means the distance past x naught. Okay. And delta t means in time delta t, in a time interval delta t. We'll show you how to get rid of the deltas here in a second. So to think about the deltas, let's go back to uniform motion for a second. Okay, back to uniform motion. What we can do is start plugging in for these delta x's and delta t's. We would say that v average is delta x. Well, I said it's the distance past x naught. It's how far you get x as a function of time past x naught. So you could write that as x minus x naught. And delta t, well, that's just delta t. Let's keep calling it delta t. Now let's solve this for this x as a function of time, because that's what we talked about in the last part, right? So we just multiply both sides by delta t. That gets rid of that. So it would be delta t times v average equals, that's a dot, I mean multiply, equals x minus x naught. X naught. And then if we wanted to solve that for x, we would just add x naught to both sides. We just bring that over here. And what would we have? We would have x equals x naught plus v average times delta t. Well, that seems kind of familiar. That's what we derived last time, right? Except last time we just called this v, and last time we just called that t. So, but when you're doing uniform motion, this is just v. When you have uniform motion, constant velocity, the average is, it's always equal to its average, right? So that's why we just called that v before. We're doing uniform motion. It was not a complicated trip. It was a simple trip. And then delta t, this is also before was just t. And the reason is really delta t is the time past t naught. It's like t minus t naught. But t naught is almost always 0, right? T naught means the time when the time is 0. So it's just 0. So you can often replace t minus t naught with just t, like we did in the last part. So the point is, this definition of average velocity, if you consider uniform motion, actually matches what we did before for uniform motion. But now, let's show you the reason we have the concept of average velocity, and that is to look at non-uniform motion. Okay, so non-uniform motion, let's do two cases. Let's do whack. The first case is called whack, and we're going to draw its position time curve like this. There is x, and there is t. And it's called whack because we're going to get Hal here, and we're going to get him going at a slow velocity, and then at one point, we're going to whack him and make him go faster. Right? Let's do that one more time. So Hal, nice, he's all happy, everything's fine, going nice and slow, and then whack, faster, right? Hal went at 2 velocities on this trip. So he started out here, going nice and slow, and then whack, and he went like that. All right? So clearly, this experiment, there were 2 slopes, and there were 2 v's. So what do we do? What do we do when we have a complicated trip with 2 v's? The one thing we can calculate for the whole thing is the average velocity. So it looks something like this. If we call this v1 and this one is v2, the average velocity is for the whole trip. You say, what is the total delta x? It's that. And what is the total delta t? It's that. You just divide the total distance it went by the total time it took it to get there. Because, as we said before, VAV is delta x over delta t. Now, it is not the average of V1 and V2. You might think the name of it implies you just average V1 and V2, but you don't, because it's actually kind of weighted by time. So here I've given them both an equal time, so it kind of looks like it probably would be about the average. But you could have the case where it went fast for a much shorter time, and then you'd give more weight to V1. So by taking this total delta x and delta t, you're weighting the average by time. And then you don't have to even think about it. You just say it's delta x over delta t. You can even draw VAV. It looks like this. It's this line, right? That goes from here, total x over the total delta t, V average, right? So whenever you're considering a problem with a complicated trip, that's how you get the average. Let's look at one more case. I didn't leave myself a lot of room here, but I think I can fit in back. Right? Whack and back. Let's see, back is going to look like that. And what's back going to be? Back is going to be Hal is here, he's happy, everything is fine. And now let's start him at the origin, all the way over here. Hal's at the origin. And he's moving along nice and fine. He's going kind of slow, and then whack, and he goes back to the origin, right? So here, what would that look like? Let's think. He started at the origin, and he was going kind of slow. Everything's fine. And then I hit him at a higher velocity, but backwards, right? He's going the negative x direction. That means his velocity is negative. That also means his slope is negative. So it looks like this. So he went V1 and V2, where if we were giving it numbers, V2 would be a negative number. So you could say, what was the average velocity of that trip? Well, average velocity is always delta x over delta t. Here's delta t. Right? Delta t is a number. What is delta x? Delta x is 0. It made some progress along x positive, but then it came back, and delta x equals 0. Therefore, the average velocity of this trip is 0. Even though it was moving the whole time, the average velocity is 0 because it had no total distance that it moved. So in physics, we call that displacement. Okay? So distance is kind of how far it went along a path, but displacement is the difference in the position from the beginning, between the beginning and the end. So all this time we've been doing x, we've been thinking about displacement. So we'll get more into the specific differences between distance and position and displacement as we move along. But this is a case where you really have to see it. You have to realize there was no displacement here. It ended up right back where it started. So that's how you use average velocity. Let's see how we use it in a few problems.